We looked at how the smart timer module works, but that's pretty much a repeat of what was done earlier. The only thing that we have done differently over here is we sort of understood a little bit more about the kinds of APIs that are used and how we can actually go about creating a smart timer driver, right, which can be automatically mod probed by looking for the compatibility flags. Okay. So if I wanted to actually implement code corresponding to something like a Fourier transform, what does that mean? I could write a C program in order to do Fourier transforms, right? So I'm going to assume over here that all of you are roughly familiar with what a Fourier transform looks like. If not, then it doesn't matter. You can think of it basically as C code which works on an array of data, and it needs to perform some mathematical computations involving some complex numbers, right? And finally the output is another array of data. Okay. So the question becomes, in the drivers that we have looked at so far, I have a way, for example, of setting the period of the smart timer or the duty cycle of the smart timer. So if I have one 32-bit value that I want to write, that's easy enough to do. But let's say that I actually have a block of data that I need to transfer into my system, right? Now how do I even do this, right? Should I sort of have separate addresses corresponding to each and every individual location that's present in memory? That is of course one possibility. The problem is, if I want to expose it using something like sysfs, it starts to get a little bit more complicated, right? On the other hand, perhaps I could have some other way by which I could actually have a better mechanism where I can basically open a file and just write data into that file, and that data will get written into a chunk of locations in the memory of the system, right? That sounds like it would be a cleaner and nicer way of doing it, right? The more sort of Unix like way of doing things, where I essentially say that this entire memory block that I have corresponds to a chunk of memory, and by just opening this file and writing into it, I will end up writing data into the correct locations, right? So that, in other words, corresponds to what I am going to call over here as chunked transfers, right? I want to be able to write multiple different values into a series of locations in the hardware, right? So I need to sort of think about how my hardware design will look, right? And one way of thinking about it would be that I might have something like this. I have my FFT module, right, which is essentially connected to the AXI bus. But what I do is that I basically say there is a memory block out here, right, where I have certain things like, for example, this might be my control register which allows me to start or stop the system. This might be a status register which tells me whether the computation has started or not. And then over here I have what I call data, right, in which case maybe one of the things that I could do might be something like, my status register corresponds to the address 0, the control register corresponds to the address 4, the data register maybe starts from an address 100. Why 100? Just a random number that I picked, right? I don't want to start from 8 and then increment from there. I want it because it's a large chunk of data that I want to write. So I'll start from 100 and then say 104, 108, 10C, 110, and so on, right? All of these essentially correspond to data, right? So the interesting thing is, what that means is that from a hardware point of view, I can actually pick up each of these different memory locations. I can just write an array of data almost as if I'm just writing into an array of locations in memory. The point is, I also want this to look like a file, right? And the question becomes, how do I do this kind of thing where I essentially make the system look like a file to the user of the operating system, but at the same time it actually has a direct way of accessing memory, right? And what we'll see in the demo that I'm going to show you is that it's quite possible to sort of effectively fool the system into reading what is effectively numbers written as normal text, converting them into a format where there are a series of numbers and writing them into locations one after the other, right? This becomes very useful when we are trying to, for example, work with large chunks of data, as an example being the FFT, right, which at some point we will write code for. Now, why would the FFT be something that we might actually want to create in hardware? It's actually an excellent candidate because it turns out that if I write C code for the FFT, it works well. It is numerically intensive, it is able to perform the computation quite well on most ALUs, but the FFT by its very nature also has a very high degree of parallelism. What I mean by parallelism is, it's possible, let's say I'm trying to do a 32-point FFT, I might actually be able to put 32 multiplication blocks inside my FPGA hardware and finish my entire FFT within a few clock cycles rather than hundreds of clock cycles, maybe a few, just possibly even less than 10 clock cycles, right, rather than going for hundreds of clock cycles, which is what will be required if I am writing it as code on the CPU. This is sort of an excellent example of how we can use hardware in order to accelerate a computation. What happens, of course, is I still need this bottleneck, which is, how do I get the data into my hardware unit in the first place, then I perform the computation and then I pull the data back out. Okay, so as we will see later when we get to this, you might end up in a scenario where it turns out that this part of the module, which we are going to write one word at a time into my hardware, is going to actually become my bottleneck, but at least it's a way of solving the problem. So let's try and go one step further. As I said, one of the things that we may want to do is to actually be able to bulk transfer data. And for that, what I'm doing over here is I've got this FFT block demo module, which again you can see has a similar structure at a sufficiently high level if you look at it, right. So for example, I have a few offsets that are defined over here. I once again have something called a control register, a status register, right. All of these right now are meaningless. All that I can do with these registers is I can write data into them and I can read them back, because as far as Renode is concerned, it will treat them as memory blocks. Later on, we will see how we can actually get Verilog and integrate it along with this so that we can do a full system level simulation, right. So I can also have the number of values that I have written up to this point being retrieved by reading this len variable, right. And of course, I want to be able to actually write the data. And what I'm going to do over here is I say that the offset corresponding to the data starts at this address 100 hex, and then from there onwards I can have like 64 32-bit values written in. Now the pattern that I'm going to assume as and when we go forward is that I'll actually be doing 32-bit numbers which are interleaved. So I'll have the first real value, then the imaginary value, then real value, imaginary value, and so on. Okay, but all that comes later. Right now this is just a toy example, right, just to show that I can write data and read it back. So let's look at this. Our FFT demo itself has pretty much the same structure as before. There's just one additional thing, I have defined one variable over here called pause. Now why do I need this, right? Remember what I said about not using global variables. I could have defined a position, which is the number of values that I have written into the system so far, as some kind of a static variable or a global variable in this module, but that's not a good idea in general, right. As we discussed earlier, right, it's not portable, it can cause problems with memory leaks and so on. It's better to sort of put it into the device struct. So I define this device struct and I say that there is this pause which corresponds to what I need to use out here. I also have this mutex. We'll talk about that a little bit later, but mostly for the time being we can ignore it, right. We have a few things. For example, you'll notice that there is this status underscore show that I have defined, very similar to the control show, control store, status show, status store, and so on that we discussed in the case of the smart timer. But you might notice that I don't have a status underscore store, and I have defined this device attribute as RO, or read only, right. So this is a nice way by which I can basically say that the status is a read only thing. If I try actually writing to the status, I should get some kind of an error from the kernel. Okay. Now the len on the other hand, right, is the length or the number of parameters, the number of values in that data that I have written in so far, right. What do? I basically, if somebody asks me what is the current value of len, it will actually allow me to, it will read out that value from this particular memory location, convert it into a hexadecimal number and return it to me so that I can read it. And yes, once again I have defined this as a read only attribute, right. And now what I have is, I have another function for control store, right, where you will find that there are a couple of different things I can do. I can, for example, write in the string reset. I can echo that into my control register, and what it says is, if whatever it got from sysfs is the string reset, then it has to go and do a few things which basically say, reset the value of the length, right, come back and basically start once again. Now whenever you do something of this sort, it sort of adds this what's called a mutex. For the time being, I'm going to ignore this. We'll get back to it when we talk a little bit more about concurrency, right. A mutex is something called a mutually exclusive parameter, right. It allows you to make sure that two things cannot write into the same device at the same point in time, or cannot in general access the same device at the same point in time, right, or the same location or the same point in memory, right. So the moment I call this mutex lock and then I start executing instructions after that, I can be sure that there is no other concurrent process, some other part of the kernel, that's also going to be accessing these same memory locations or calling this same part of the code. Okay, so we require that for safety purposes, but apart from that, I'm just going to leave it. I'm not going to sort of get into more details on that, right. So the interesting thing here is, you might notice that previously what we did was, when I wanted to write control, I would directly write a number, where I would need to decide what are the strings, what are the bits that need to be set or reset, and I need to correspondingly have each of those appropriately set up. Whereas now what I'm saying is, I can actually write a string like start, and the kernel will then figure out that I'm actually trying to start this particular module, convert that into an appropriate bit mask, write this value into the corresponding memory location, and basically update things as I need over here. Okay, so this is a different way of handling the approach, where sysfs gives you an even more file-like interface, where I don't really need to compute these numbers which are required for starting or resetting a given peripheral. Right. All right, going further, right, there are a few different things that you can do there. But now you will notice that this is also interesting. This particular attribute control is defined as write only, right, and as we will see later, this means that if I try reading from that control register, I'll actually get an error, right. So this is interesting. Why would I ever have write only? I never have the concept of something called write only memory, but it is possible to have a write only address where I can use it for control signals. I basically send information into the system, but I do not expect to read anything back from the same memory location. Yeah. Finally, we have this other set of functions called vector, right? So vector store, and this is, as you can see, a lot more complicated in terms of what the function looks like. It actually goes through and it is trying to parse through whatever string that you have specified. Okay, so I'm not going to walk through each and every step over here. But what it does is, effectively it allows me to, for example, write a number into this vector file, right, and that value will basically get written into the location FD base, that is the starting address, plus the offset corresponding to the data, which was that 0x100, plus this FD pos into the size of an integer. What is FD pos? What happens is, every time I get a number from here, FD pos gets incremented by 1, right, and every 2 times that I have got, or rather for every 2 values, that is one real, one complex value that I write, I basically go and update the length or the number of values that have been written in so far. I increment it by 1, or I basically update that value to whatever it is. Okay, now as you will see, this is quite interesting. What has happened over here is, this vector variable has now been, or rather this vector file has been defined in such a way that I can keep writing numbers into it one after the other, and this function will actually take care of taking each of those values and putting them into successive memory locations one after the other, right. So if I want to, for example, fill in 32 complex numbers, I could just take a file which consists of many different numbers one after the other, 64 different numbers, real and imaginary, right, and just do a cat and dump that file straight away into this particular virtual file, the vector file, it will end up populating directly into my hardware. Okay, let's take a look at how that exactly works. But once again, the thing to notice over here is that's also defined as a write only attribute. Okay, so yes, we have defined the list of attributes. We have the probe function, which looks exactly the same as what it was in the case of the smart timer. We have the remove function. We have a compatibility string over here, which basically specifies the same thing as what we have in our device tree. And finally, we define the platform driver and we call the module platform driver. Okay, so at some level similar to our smart timer driver, but with a few interesting differences. Let's go and look at what that actually implies for us, right? So I still have my Linux system booted up here, and I'm going to now look at what does this correspond to in terms of the FFT module, right? So let's go look at the same sysbus platform, devices, right? And what I can find is that there is another peripheral over here at the 7000 1000 address. So let's go look inside that, right? And you can now start to see that there is a variable called control, or rather a file called control. There is another file called len. There is a file called vector, and there is a file called status. Okay. Now I can, for example, look at what is the value of len, right? And I can just cat the value of len and it shows me that it is 0. I can check the value of the status and it shows me that that is also 0. Both of these were defined as read only, right? But now if I go and look at what is the value of control, it tells me that permission denied. Okay, and this is an interesting error message because you might have generally seen or rather understood the way that Linux works is that the root user, the super user, there's no such thing as permission denied, right? I mean, you are never sort of not allowed to do something as the root user. Well, this is an example of permission denied because fundamentally what is happening over here is the kernel is saying that there is no way of actually reading this file. So if you try reading it, the message that it gives you is permission denied, even though that's not strictly speaking what's happening. It's simply saying that it couldn't even open the file, right? It interprets it as meaning that you are not allowed to open the file. Well, that was because I did not write a control_show function, right? And basically declared it as write only rather than read write. Okay. Similarly, if I try doing this for vector, I'll find that I get the same permission denied error message there as well. Okay. Now what if I try writing, right? I can, for example, do something like echo 1 greater than, I can try writing this into the control, right? And when I do this, it doesn't complain, it also doesn't show anything much, except that when I go back to my Renode over here, and if I go look at this particular, the memory location corresponding to the FFT 00 and FFT 0, I can read the word present over there. And it now shows the value 1, right? Because I just wrote 1 into that particular memory location out here. Okay. Can I do the same thing with status? No, it turns out permission denied over there, right? Because status has been declared as read only. Okay, but now can I also do this with vector, right? And it turns out that yes, it actually allows me to do that, right? And now I can go read, right, from this memory location. Remember what was the starting address that I had for the data? It was 100, right? So the 1000 plus 100 hex, right? And I can see that yes, I have now written this value 1 into this memory location. What if I now go and write the value 2 into vector, right? I go back and read the value at the same memory location, it hasn't changed, it's still showing 1, but the next memory location is now showing the value 2. So remember what we saw in the code itself, right? The way that this vector store function works, it keeps track of the FD position, right, and makes sure that it writes and increments that FD position. So the first time around it writes into location 0, next time I write it writes into location 4, which is the next address, next into location 8, next into location 12, and so on, right. So if I go back here and I continue with this, what I'll find is that I can basically keep writing different values over here, right, and each of those essentially corresponds to, well, yeah, so at location 8 I now have the number 3, and at location C I find that I have this number 4, right. The next location that would be valid would basically be this 1 0, where it turns out that the value is still 0, because by default Renode initializes the memory to have values 0, okay. Now it's not just that, I can actually do something a bit more interesting out here, where I can actually have a string which looks something like this, right, 5 6 7 8, and at one shot I can basically write all of this into the vector, right. This worked, and now if I go look at this point over here, I find that yes, that number has got the value 5, this one has got 6, 8 has got the value 7, and C has got the value 8, okay. So at one shot, in other words, by having a string of this sort, I was able to write multiple values into it. Very convenient for human beings, not particularly good from the point of view of the kernel, because what it has to do is it has to take a string, read numbers out of it by using the kstr2u32 function, convert them into unsigned 32-bit numbers, and then write them into the appropriate location. So actually speaking, quite inefficient, right? In practice, we would almost never use this. What we would do instead is to actually have some kind of a binary format interface, where I can just take data that is already stored in binary format and do the same thing, where I copy it into a particular file, right? I just take data from one file and then cat it into another file, and sure enough it will make sure that all the data gets stored in the proper locations. Now there's one more interesting thing that you can see over here, which is, so far we have been just writing values into vector. What happens if I now go and look at the value of the length variable? Right. You can see that this has now got the value 4. Now why 4? Because the number of values I've actually written is 8, but it's treating these as 4 complex numbers, right? Every pair of numbers is treated as one complex number, and therefore even though I wrote 8 values, 1 2 3 4 5 6 7 8, it basically goes and changes the length only up to 4. The interesting thing is I can just rerun this command, and now if I look at len, it has become 6. Another 4 values have been written in, right? So the reason for showing all of this was the flexibility that the virtual file system provides us in terms of how we can communicate with devices, right? We can do a number of different things, and how we interpret what is actually being communicated to us, or how the user, the end user, communicates with the device, right? We can basically write any code that we want in our device driver, well, within limits of course, right? But we can, for example, accept data in ASCII format, convert it into numbers and store it. We can take the data which is actually present inside the system and display it in some other format which is useful. I can, for example, even have a device driver where the entire video memory corresponding to a system is exposed as a file, which means that by just taking an image and doing a cat into a particular set of memory locations, it will be like I display the entire image, right? So there are a lot of interesting things you can do once you start playing around with device drivers at the kernel level. As far as we are concerned, the main purpose of what we are looking at is to understand the basics of what it means to have a platform based device driver, and what are a few different ways by which we can use this when we want to interface with hardware, right? Because eventually our goal is to sort of write custom hardware and have these drivers that are then able to interface with these systems.